Hello everyone, I am Sir Athan. In this video, we are going to talk about triple integrals in cylindrical and spherical coordinates. Let's start with cylindrical coordinates. Suppose we have a point P with coordinates x, y, and z. We know that this point has a corresponding coordinates in the cylindrical coordinate system, and that is given by r, theta, and z. Let us have a recall. Suppose this is our point P with Cartesian coordinates x, y, and z. Now, if we draw a line parallel to the z-axis, passing through this point, and we get the intersection of that line with the xy plane, and let's say we denote this by P prime. The distance of P prime from the origin is r. The angle formed of this line segment with a positive x-axis is represented by theta. Z is actually the distance of the point P with the xy plane. And that's how we convert a point P from its Cartesian coordinates to cylindrical coordinates. Our idea in this section is we have to convert our iterated triple integral in Cartesian coordinate system to its iterated triple integral in cylindrical coordinate system. In general, suppose we have this iterated triple integral in Cartesian coordinate system. That is also equivalent to this integral written in Cartesian or cylindrical coordinate system. Note that dv in cylindrical coordinate system is written as r dz dr d theta. They are bounded by the same solid, but the solid here on the right hand side is actually represented by the cylindrical coordinates. Let us have an example. Use cylindrical coordinates to find the volume of the sphere of radius a units. By this time, I hope you already know how to set up a triple integral in Cartesian coordinate system that will evaluate the volume of the sphere. And you may verify that this is given by this expression. Now, our goal is to set up first an iterated triple integral that will determine the volume of the sphere of radius a units. Alright? So consider this sphere. Okay? Our idea is to convert all the Cartesian equations into its cylindrical equations. Take note that this equation, we only consider the upper hemisphere, which is above the xy plane. So this figure or this solid can actually be represented by this equation. Z equals square root of a squared minus x squared minus y squared. Converting this into cylindrical system, that could be written as z equals square root of a squared minus r squared. So from our expression a while ago, the height function for the cylindrical coordinates is given by this one. z equals square root of a squared minus r squared. So in our triple integral, the innermost integral that is governed by the variable z. So the bounds for z here is 0 to square root of a squared minus r squared. The two outer integrals can be represented on the xy plane. Take note, if we have this sphere, the region considered on the xy plane is actually a circle of radius a units. So if we have a circle of radius a units in Cartesian coordinate system, that is represented by x squared plus y squared equals a squared. Converting this into cylindrical equations, or more popularly known as polar equations, that could be written as r equals a. So going back to our triple integral, our middle integral, the variable to be considered is r. From the xy plane, the boundaries for r here is 0 to a. The outermost integral is governed by the variable theta. That is the angle formed in the two-dimensional system. So since we have a circle, we only consider a revolution of this circle. So theta will be bounded from 0 up to 2 pi. And of course, in our integrand, do not forget r. And since we only consider here the upper hemisphere, multiplying it by 2, we get the volume of the sphere. So the volume of the sphere is given by the integral from 0 to 2 pi times the integral from 0 to a times the integral from 0 to square root of a squared minus r squared of r dz dr d theta, and multiply it by 2. And if you simplify this integral, you should check that this should be equal to 4/3 pi a cubed. Let us have another example. Set up using cylindrical coordinates this iterated triple integral of x squared plus y squared dv, where S is the solid bounded by x squared plus y squared equals 9, and the planes z equals 0 and z equals 4. As a solution from this example, take note that our iterated triple integral is written in Cartesian coordinate system. So our goal here is just to convert the Cartesian equations into cylindrical equations. Look at the integrand that is given by the square root of x squared plus y squared. And we know if we convert this into cylindrical equations, x squared plus y squared will be written as r squared. So, square root of x squared plus y squared will be represented by r. dv, we all know that that is equivalent to r dz dr d theta. And finally, we just have to determine the bounds of these three variables that we have. So the solid being considered is bounded by this equation, x squared plus y squared equals 9, and the planes z equals 0 and z equals 4. Take note that the equation given by x squared plus y squared equals 9 is actually represented by a right circular cylinder. So in 3D space, so that is a right circular cylinder. The lower bound of that cylinder is given by z equals 0, and the upper bound of that cylinder is given by z equals 4. And that actually determines the bounds for z. So our innermost integral is given by 0 to 4. I mean, the bounds for the innermost integral is 0 to 4. Now let us determine the bounds for r and theta. From this three-dimensional space, take note that if we project this graph on the xy plane, we will just be having a circle given by x squared plus y squared equals 9. And take note that its corresponding polar equation is r equals 3. So our radius function, r, is bounded from 0 to 3. So that will be the boundary of the middle integral, 0 to 3. The bounds for theta, since we have a circle, the entire circle, therefore the bounds for theta is from 0 to 2 pi. Hence, this integral, iterated triple integral, in cylindrical coordinates is equivalent to this integral in Cartesian coordinates. Therefore, this is the triple integral in cylindrical coordinates that we are looking for. Now let's talk about spherical coordinates. Suppose we have a point P with coordinates x, y, and z. These can also be represented in terms of spherical coordinates, and that is given by rho, theta, and phi. With these conversions, as I recall, suppose we have a point P with coordinates x, y, and z in Cartesian coordinate system. The distance of this point from the origin is rho. If you draw a line parallel to the z-axis passing through this point, and we take the intersection of that line with the xy plane given by P prime. The angle formed of this line segment with a positive x-axis is given by theta, which is also similar to theta in the cylindrical coordinate system. The angle phi here is represented by the angle formed by this line segment with the positive x-axis or the positive z-axis. Take note here that the angle phi will range from 0 to pi. To express the triple integral in spherical coordinates, we will be using this differential for v, that is rho squared sine phi d rho d theta d phi. In general, the iterated triple integral is given by this expression, f of rho sine phi cosine theta, rho sine phi sine theta, rho cosine phi times rho squared sine phi d rho d theta d phi, where the solid S here is represented by the spherical coordinate system. Let us have an example. Find the volume of a sphere of radius a, and in this example, we will be using spherical coordinates to derive the volume. We have already seen its volume in terms of the Cartesian coordinate system. We already saw the volume in terms of the cylindrical coordinate system. In this example, we will be using the spherical coordinate system. Just do not forget the expressions we have a while ago in setting up the iterated triple integral in spherical coordinate system. Take note, our dv is, again, rho squared sine phi d rho d theta d phi. Now let's look at the bounds for the innermost integral, and that is governed by this variable rho. From our discussion a while ago, rho is actually the distance of the point from the origin. Since we have a sphere, and take note that the equation of the sphere in the Cartesian coordinate system is given by x squared plus y squared plus z squared equals a squared. In spherical coordinate system, this is given by rho equals a. Meaning to say, any point of the sphere has a fixed distance from the origin, and that is given by rho equals a. Therefore, the bounds for rho is 0 to a. Now let's look at the bounds for theta. The bounds for theta can be seen on the xy plane. Again, looking at this sphere, the graph of this projected on the xy plane is actually a circle of radius a units. Theta here is the angle revolved by the point or by the points on the xy plane. So the bounds for theta is from 0 and making one revolution to 2 pi. Therefore, the bounds for theta is 0 to 2 pi. The bounds for phi, take note that phi is the angle formed by the line segment passing through the point and the origin with the positive z-axis. So let's say this is a point on the solid. We form a line segment passing through this point from the origin, and we take the angle formed by this line segment with the positive z-axis. And take note, this is represented by phi. And this point will range from here, the intersection with the positive z-axis, up to here. So phi here, the bounds are 0 to 5. And finally, this is the volume of the sphere written in spherical coordinate system. And you should verify that when you simplify this iterated triple integral, you will get 4/3 pi AQ. Let us have another example. Set up the iterated triple integral in spherical coordinates, where S is the solid enclosed by x squared plus y squared plus z squared equals 4. Before we determine the bounds for our triple integrals, we should convert the rest of the expressions in their spherical coordinate system. This x plus y will be represented by rho sine phi cosine theta. This is for x. For y, that will be rho sine phi sine theta. And of course, our dv, that will be rho squared sine phi d rho d theta d phi. Now, the bounds for the integral, this will be easy since the solid is just a sphere. X squared plus y squared plus z squared equals 4. Writing this in spherical coordinate system, that will be rho equals 2. So that will be, that will determine the bounds for rho. That will be 0 to 2. Since we have a sphere, so definitely the bounds for theta will be 0 to 2 pi. And finally, the bounds for phi will be 0 to pi. So this triple integral in spherical coordinates is equivalent to the triple integral in Cartesian coordinates we have a while ago. If you want to learn more about topics on Math 28, check out these videos. And don't forget to answer the exercises found in the description below. Have a good day. Bye!